Alright, silly people, here's the situation. Griffiths gives us this very basic form for a three-dimensional vector, and we're basically going to change around some of the variables a bunch, and check that if we do that, we get different vector spaces. Um, so there's a process for checking whether like a vector space is actually a vector space. Uh, Number one, the space has to have the ability to have the zero vector, right? So the way that Griffiths wrote it here, it would be 0 I hat plus 0 j hat plus 0 k hat, or just the 0 ket, right? Um, Number two, it has to be closed under vector addition or scalar multiplication. So in the case of the vector above, if we added another vector onto it, which it was just, um, let's call it bxi hat plus byj hat plus bzk hat. If you add those up, that looks like ax plus bx times I hat plus ay plus by times j hat plus az plus bzk hat, which under the rules of the the a constants just being any complex number, uh, that is still part of the vector group. So the last thing to check is that it is closed under scalar multiplication. So if we multiply some c constant, where c is also a complex number, times the vector, so that's actually ay j hat plus az k hat, then we still have to have a like a vector that's still in the group, right? So it'd be caxi hat plus cayj hat plus cazk hat. And c times a complex number is still going to be a complex number, so that is also in the vector space. So this is a good vector space. Um, then we can start getting to the actual problem, just doing all the same checks again, but setting az to 0, seeing if that constitutes a vector space. Well, let's check if it has the null vector. Um, 0 I hat plus 0 j hat. So, yeah, it has the null vector. It's just a two-dimensional null vector now. 2, is it closed under addition? So we'll have ax I hat plus ayj hat plus bx I hat plus byj hat is just going to be ax plus bx I hat plus ay plus by times j hat, which is still in the like confines of the space, so it's closed under vector addition at least. Next is it closed under scalar multiplication, so we'll do the c again, ax I hat plus c or plus ay j hat. That just looks like caxi hat plus cayj hat. So it's closed under scalar multiplication as well, so this is a vector space. Awesome. Now, does az equal 1 constitute a vector space? No. Right, it fails the first test because there's no way to get to the 0 vector out of this. You can set AY and AZ, or AY and AX to 0, but AZ is always 1, so there's always going to be a K hat. So there's no way to get the null vector, so it fails. Not a vector space. The last problem that he has us look at is if all of the components of the vector are the same. So we can write it as just a I hat plus a j hat plus a k hat. In other words, this can be written as a times I hat plus j hat plus k hat, and then let I hat plus j hat plus k hat be a new vector, which I'm just going to call v hat, right? So we were starting with 3 dimensions. We got a thing that was only 2 dimensions. That was this one. This is going to be truly just a 1-dimensional vector space. So is it closed under, so does the null vector exist? Yeah. You can set a to 0, and then you get the null vector. So it passes the first test. Is it closed under vector addition? If we say a v hat plus b v hat, we just get a plus b v hat. So it's closed under there. Is it closed under scalar multiplication? Yes, it's closed under scalar multiplication. So this is a vector space as well, just a 1-dimensional one. All right.